Hello everyone and welcome to Network Playroom. This is the first video in the Christmas calendar series and I'm back with my beautiful Christmas tree network topology. So I've made a small change here and I've added the router names to the topology to make it easier to follow. And in this video we're going to talk about basic routing concepts and what are the first things to consider if IP communication fails. There are three fundamental routing principles introduced in the Cisco IP Routing book by Alex Zinin, and they summarize the core mechanics of IP routing. Now I've written the principles down here on this list under the Christmas tree diagram, but we'll look at those principles in more detail. So let's start with the first one. Now, number one, every router makes its decision alone based on the information it has in its own routing table. And when making the routing decision, a router can use only information in its own routing table. There is no way for a router to know if its neighbors are going to make a consistent decision. The router can only think for itself. So routers route packets according to the information they have in the routing table at that specific time. So when a router forwards a packet to the next router, a router assumes that the next router will do the same, and that is make its decision according to the information in its own routing table. And only consistent routing information can guarantee a consistent forwarding decision throughout the network. So let's look at this in an example. So let's imagine that R9 has a loopback interface configured here with the address 9.9.9.9/32. Let's say it's loopback 9. And then R1 on top here wants to ping that IP address. Now, R1 really has two choices to send the packet, either out this interface or this interface. Since I haven't configured or I haven't indicated any costs on the links, we'll just assume that the shortest path is the best path, and that is what would be installed into R1's routing table. So it would want to go through R5, then R4, and finally reach R9. But R1 doesn't know if R5 would actually follow that same path. So what is meant by a consistent forwarding decision is that R5 would actually send the packet in the same way that R1 would. So there's no way for R1 to know where R5 is actually going to forward that packet. In fact, it could actually send it back to R1. This is obviously not a situation that you would want because that would be a routing loop, but technically it is possible. But yeah, that is really what is meant with the consistent forwarding decision, that the packet would follow this path from R1 to R5, R5 to R4, and then finally to R9. And then all routers in the path would make those same decisions and send the packet that way. All right, let me get rid of these ugly arrows. And then let's move on to the next principle. So number 2, the fact that one router has certain information in its routing table does not mean that other routers have the same information. So even if the nearest to the source router has the required information about a remote network, other routers on the way to the destination may not have information about it. Therefore, even if the first router forwards a packet successfully, the next router or any router on the path to the destination may drop the packet if it doesn't have enough routing information to forward it. So again, coming back to the example, so let's say that the ping from R1 gets to R5 successfully. But what about now? There's no guarantee that R5 even knows about this loopback network. So just because R1 knows about it doesn't mean that R5 does. So this is something important to keep in mind. So don't assume just because R1 learned about this network that R5 did. It is possible that R5 would not have this network installed in its routing table and therefore couldn't make a routing decision and it would have to drop the packet. All right, but then moving on to principle number 3, which states that routing information about a path from one network to another does not provide routing information about the reverse or return path. So even though all routers along the way to a destination have information about the destination network, the remote routers may have no information about how to route the packet coming back. So again, let's go back to this example. So let's say that the ping from R1 got all the way to R9, and all of these routers on the path were able to successfully route it. So that does not mean that the packet will find its way back to R1. Now let's actually think about the IP packet that R1 is going to generate when it sends that ping. So let me create another network here. So let's call this network between R1 and R5 10.1.15.0/24, and then give this one .1 and this one .5. So what would the IP packet look like? So what would be the source IP address in the packet destined to this loopback interface? Well, by default, it is the IP address of the outgoing interface. So in this case, it would be the IP address configured here. So we just assigned it 10.1.15.1. So the packet would be source address 10.1.15.1 and destination 9.9.9.9. So just because R1, R5, R4, and R9 were able to successfully get the packet all the way from R1 to R9, doesn't mean that they can forward it back, because when the ping packet is coming back, essentially this is reversed. And IP routing is destination based. So what we're looking at now is source, well, I'm going to put 9.9.9.9 here, and then put destination 10.1.15, 15.1. So now this has completely changed. So there's no guarantee that R9, R4, or R5 have a route to this address. Well, R5 would have it because it's directly connected, but R9 and R4 would need to know about this network to be able to route the packet back to R1. Okay, so in all of the cases we've discussed, the router would drop the packet if it could not make a routing decision. But lack of routing information about a destination network is not the only reason for a router to drop a packet. So for example, a router can also drop packets because the router doesn't have enough CPU time to process packets from the input or output queues. A packet is also dropped if the value of its time to live field reaches 0. So this has this is actually what ultimately prevents the routing loop from happening. So what I described earlier, that in theory, a packet could loop between R1 and R5 here. So the TTL is used to prevent that. And then another reason for a router to drop a packet is the inability to fragment an IP packet while trying to send it through one of the router's interfaces. So these are some things to keep in mind when you're troubleshooting failed IP communication. So there could be several things that can be wrong for the IP communication to fail, and you must consider all of them. But I think the most common one, or at least personally, when I was learning about IP routing, I stumbled upon principle number 2, and that just because one router had information about a network, it didn't mean that another router, usually a neighbor router, would have the same information. So I personally really struggled with that in the beginning. But yeah, that's it for this video. Thank you for watching, and I'll see you in the next one.